It's maybe the moment to start the afternoon session with Matthias Gaberdiel, who will speak about the string dual of free maximal supergang wheels. Please.
Okay, Sanjay, thank you very much. It's a great pleasure to be here. I wish I could be in Moscow physically, but some of these days, hopefully. Okay, so I want to talk about work that really goes back a long time, building on work I've done with Rajesh Gopakuma for the last almost 10 years or so, but more specifically about some recent development. So let me remind you about sort of the basic setup of the AdS CFT correspondence. So what's important to take away is the relation between the parameters of string theory on one side and that of the dual CFT on the other. So the rank of the gauge group is related to the radius in Planck units to some power, and the TUF parameter, that's the effective coupling constant in the large n limit, that's related to the radius in string units to some power. And then the string coupling constant is related to the Young-Mills coupling constant. Now, in particular, if you're interested in trying to prove the AdS CFT correspondence, one corner you may be interested in is in the corner where the gauge theory is weakly coupled, which means that what I have in mind is we're going to take the large n limit as always, but now we are thinking of the regime where the TUF parameter, the effective coupling constant at large n, is small. And what this dictionary tells you is that corresponds to the regime where the radius in string units is also small, which is another way of saying that the string is very, very large relative to the space, to the size of the space in which it propagates. So this is what's sometimes referred to as the tensionless limit of string theory. And it's the regime of string theory that you would believe to be dual to free or weakly coupled gauge theory. And that's these old ideas. So Bort Sundberg, I think, was probably the first to really put his finger on that. And then there were subsequent developments. And that is really something that many people in the audience are familiar with, because the tensionless regime of string theory, that's the regime where string theory is very stringy, very far from the supergravity regime. That's the regime where you expect these Vasiljev type higher spin symmetries to emerge, because if the string tension is very small, then the excitation modes of the string are essentially massless, and the spectrum will have infinitely many fields of higher and higher spin. And you would believe that that's the regime where you have a higher spin type description of string theory. In any case, that's what the string theory dual of weakly coupled or free super Young-Mills theory looks like. And in some sense, it's what you believe to be the most symmetric point in the moduli space of string theory. So that should be somehow the maximally symmetric phase. And the string backgrounds we are more familiar with, you should think of as being arising upon some Higgs mechanism, where some of the massless degrees of freedom acquire mass, for in particular the excitation modes of the string become massive. So that's some sort of Higgs point, but the tensionless point is really the most symmetric point you would expect this theory to have. Now, obviously, the dual super Young-Mills theory is very simple. It's free. So you could ask yourself, what's the redeeming feature from the point of view of string theory? I mean, if you look at it from supergravity, it looks super complicated, but there should be something simple about it from the string perspective. And one idea you could have is that what's special about this theory, that it will also have a very simple description from the point of view of the worldsheet. Certainly, you would expect it to be a solvable worldsheet theory, maybe even a free worldsheet theory, in some sense reflecting the enormous symmetry which free super Young-Mills theory has and which the string background somehow has to inherit. So this is sort of the framework in which we try to find a concrete incarnation of the AdS CFT correspondence that would allow us to prove it. The idea is we're going to look at weakly coupled super Young-Mills, and we are trying to identify the simple worldsheet description that describes tensionless strings on AdS. Now, this program, and this is in some sense what has been motivating us for the last few years, is actually quite concretely realized in the context of AdS3. So if I may just remind you what the statement about the AdS CFT correspondence for AdS3 is, it's the conventional wisdom that string theory on AdS3 cross S3 cross T4, say, I mean, there are other backgrounds to consider, but that's in some sense the simplest one, is this string theory is believed to be dual to a conformal field theory that differs from the symmetric orbifold of T4 by some exactly marginal deformation. That's the generally believed statement about the AdS CFT duality for the case of AdS3. So if you want to sort of connect this to that, the first question you have to ask, what's the analog of weakly coupled free superangles? And the obvious idea is that the analog of free superangles is the symmetric orbifold theory itself, because that goes as close as it goes to being a free theory. So that should be, in some sense, the simplest point in this moduli space. So this general philosophy should imply that it has a tensionless string dual. And tensionless should mean, as I said before, that the space is small in units of the string, i.e. that the string is very large in units of the space. And if you think about it from what this means in, say, this Wess-Witten type description of AdS, that should mean that the flux is very, very small. So this slide summarizes a lot of work, but what the upshot of that analysis was that there is actually a very simple worldsheet description. It's given in terms of 4 symplectic bosons and 4 fermions, describing the AdS3 cross S3 piece. That's in some sense the free field realization of the hybrid formalism of Berkowitz, Swaffer, and Witten that was designed to describe string theory in AdS3 cross S3. And if you're sitting at this level 1, then it has a free field description in terms of these 4 symplectic bosons and 4 free fermions. I'll explain later on what these really are. And what we've shown is that if you include the spectrally flowed representations, which is an idea that goes back to Maldacena-Auguri and even further to Henningsen et al., then you can actually match precisely the single particle spectrum of the dual symmetric orbifold from this worldsheet description. And furthermore, you can reproduce the correlation function of the symmetric orbifold from correlation function of this symplectic boson and free fermion field. So that's an incarnation of this idea, namely the analog of free superangles has a free field worldsheet description. And we've actually managed to prove this to a very large extent. We've really quantitatively managed to match the spectrum and the correlators. And this looks like a very solid piece of evidence for the fact that, at least in this context, this idea is correct. Now, the recent leap of faith we've been taking is that we've been asking ourselves, what could be the situation for n equals to 4 superangles in 4 dimensions? Now, by the same philosophy, it should dual to some tensionless strings on AdS5 cross S5. And if you're brave enough, you may think that maybe that should also have a free worldsheet description. And what we've proposed is that basically, in order to go from AdS3 cross S3, you want to replace this PSU1,1/2 by PSU2,2/4, because that's the global symmetry of n equals to 4. And what this basically means is that you should double the degrees of the number of symplectic bosons and the number of free fermions. So this is our proposal. Our proposal is that the string theory dual of free superangles has a concrete solvable worldsheet description in terms of 8 symplectic bosons and 8 free fermions. Just like for the case of AdS3, you have to include the spectrally flowed representations. That's where the real physics comes from. And then this is the one point we haven't entirely understood, but we propose that there is a natural quantization scheme, which we believe will come from first principles once one understands the cohomology of this sort of analog of the Berkowitz-Swaffer-Witten theory completely. But we propose there's a natural quantization scheme that I'll explain to you on the next few slides. And it leads to a reduced model whose spectrum matches exactly that of free n equals to 4 superangles. So if you believe that this quantization is the right idea, and I'll spend most of my talk trying to motivate it and explain it to you, then this leads to a worldsheet theory that at least reproduces correctly the spectrum of free n equals to 4 superangles. And therefore, given the fact that it's a natural generalization of AdS3 cross S3, maybe has a pretty good chance of being actually the string theory dual of free superangles in 4 dimensions. So let me explain to you a little bit more of what this symplectic boson and free fermion theory looks like. So the one way to think about it is that you should interpret the different fields as components of some ambitwistor fields. So this is sort of similar to the sort of theories Berkowitz has been proposing to describe string theory dual of free superangles. So you have some symplectic boson, a pair of symplectic boson. So alpha runs over 2 values. The alpha is basically an SU2 spinor index, and the alpha dot is another SU2 spinor index. And then you have 4 fermions that sit in the vector representation of SU4. And these are the commutation relations. So this is really a free field theory, right? So it's just the commutators are exactly like they look for a free field theory. For the fermions, that's exactly what they look. For the bosons, it's a bit funny because normally you would expect here the mode number to appear if it's spin 1, but these are also spin 1/2, and that's the reason why they are symplectic bosons rather than the real bosons. So these are the fields that make up this worldsheet theory. So it's a super explicit. There's an overall U1 field that you need to gauge. That's exactly analogous to what you have to do in AdS3. And then our postulate is that once we incorporate spectral flow, and I'll spend the rest of the talk explaining to you what spectral flow is and how it arises, there's a natural set of modes that survive after what you believe to be the correct quantization scheme. And these are basically half the symplectic bosons. So there are only 4 symplectic bosons and 4 fermion modes that survive. And their mode number sits in this funny wedge between W-1/2 and -W-1/2. That's why we call them the wedge modes, because the mode number is sort of bounded from above and bounded from below. And the claim is that after you've imposed this physical state condition, these modes act on non-trivially on a spectrally flowed vacuum. They basically just produce a Fock space, and their commutation relations are essentially trivial because they are sort of 1/2 of the set of modes, and they commute among them or anti-commute among themselves. And then the second part of this postulate is that on this resulting wedge Fock space, we need to impose some residual gauge conditions. One is this leftover condition from this U1 field that we have to set this U1 field to 0. And the other one is some sort of L0 light cone-like constraint. And then we claim, and we have by now proven, that the resulting spectrum reproduces exactly that of free n equals to 4 superhang-mills in the planar limit. Actually, you can understand why this works in relatively elementary terms. So let me try to walk you through the argument. The idea is that, sure.
You write here that this looks like that you write that this is a postulate, and my question is, to what extent this is imposed by hands? And probably you have told that I missed. I mean,
right. So maybe you ask this question again. I mean, this is to be the sort of bird's eye overview. Then I'll explain to you later on why we get there, and then we can come back to discussing whether that's a reasonable proposal or not.
Okay.
Because at this stage, I can't really explain to you the detail without giving the rest of my talk. So let me first explain a little bit more in detail, but let's just take it for the moment as given, and let's see what it would imply. So the idea is that these wedge modes, so the ZIs are just collectively describing these modes, you can think of as being the momentum modes that via a Fourier transformation would look like come from position modes. So they're really W position modes. And if you do this inverse Fourier transformation or Fourier transformation, then these position modes have the property that they only talk to one another if they sit at the same position. So J labels the position, and you can think of this as W points along a spin chain, so to say. And then the residual gauge conditions basically imply that the Cn condition for n greater or equal than 0 basically imply that if you also Fourier transform it, that at each side, this corresponding operator is set to 0. And then if you know a little bit the representation theory of PSU 2,2/4, you may have recognized that these modes, if you just let them act freely, they basically, if they were just 0 modes, they would give you the singleton representation of PSU 2,2/4, provided you impose the condition that the central term is equal to 0. So what this basically amounts to is the fact that at every site J, you're going to have a copy of the singleton representation. And this condition will impose that these W copies of the singleton representation must be invariant under cyclic rotation of this W field. So what you end up with is the W-fold tensor product of the singleton representation of PSU 2,2/4 subject to a cyclicity condition, and that is known to reproduce the spectrum of free n equals to 4 superhang-mills. So once you accept these postulates, it is relatively easy to see that this reproduces the correct spectrum of free n equals to 4 superhang-mills. So the question is, how can we justify that these are the right postulates? So this is what I want to do in the following. But before I get there, I just want to remind you what this means is that the W spectrally flowed sector will reproduce all the traces with W letters, where each of the insertions is basically one of the possible n equals to 4 fields. And the cyclicity is the L0 condition, and the fact that at each of these insertion points, you put, you satisfy this relation basically means that at each of these points, you insert one of the possible fields of n equals to 4 superangles. So this, apart from the fact that I haven't justified this quantization condition, this certainly ties in with the many ideas people have had. This really looks a little bit like a string bit picture, where the string is made up of W bits. And at each of these bits, you basically have a twistor valued string. So the novelty relative to what people tried before is that these string bits are really twistor valued. And then somehow they're combined together in such a way that they reproduce the spectrum of free n equals to 4 superangles. Okay, so this was to give you the bird's eye overview. So now I want to justify a little bit how this works a little bit more technically. So let me first review how this works for AdS3, because what we're going to do is a carbon copy of what happened in AdS3. And for AdS3, we can really prove this very concretely. So for AdS3, as I said, we are looking at this k equals to 1 theory. That's most easily described in this hybrid formalism of Berkowitz, Waffer, and Witten. And then what you end up with is the Wessel-Witten model based on PSU 1,1/2 at level k, together with some topologically twisted sigma model. And for generic levels, this description agrees with the usual Neveu-Schwarz-Vermont description, Aldemar-Dassino-Oguri. So this is commonly believed to describe correctly string theory in AdS3 + 3. Now, what's special at level 1 is that this theory has a free field realization in terms of 4 symplectic bosons and 4 real fermions. That's just a feature of this U1,1/2 theory. And again, they have slightly different names than what I had before, but they satisfy exactly the same sort of commutation relations we had before. Now, the generators of the U1,1/2 algebra are bilinears in these free fields. And in order to reduce this to P as U1,1/2, you have to gauge by a diagonal U1 field, and this diagonal U1 field takes this form. It's basically just the diagonal combination of the 2 sets of fields. Now, this theory only has, so if you start out with, you would look at the highest grade representations. There are 2 of those. Either you have a Neveu-Schwarz sector where all fields are half integer moded, or you have a Vermont sector where all fields are integer moded. The positive modes annihilate the ground state. And if you look at this representation in the Vermont sector, the ground states form a representation of the 0 modes, and that gives you what you would call the singleton representation of PSU 1,1/2. That's the natural analog of the singleton representations of PSU 2,2/4. Now, the worldsheet spectrum following Dassino-Oguri and Henningsen et al., the worldsheet spectrum doesn't just consist of this highest grade representation, but you have to include these spectrally flowed images. And spectral flow simply means that you use an automorphism of the free fields. You can write this in terms of U or PSU 1,1/2, or you can directly formulate it in terms of the free fields. So this is an automorphism. So the tilde modes satisfy the same commutators as the untilde modes, because those that get coupled together get shifted in opposite ways. And the idea is you take the Vermont representation and then you apply spectral flow to it. And what you mean by that is you consider the Vermont sector representation with respect to the tilde modes, and then you interpret it in terms of the untilde modes. And what you will see, and I'll explain this in more detail later on for the PSU 2,2/4 case, that means that you end up with not highest grade representations with respect to the untilde modes, because some of the positive modes don't annihilate anymore. And the claim is that you should take this Vermont sector plus all its spectral flowed images. That's exactly what reproduces the analog of the Dassino-Oguri spectrum K=1. Now, this PSU 1,1/2 theory has many, many null vectors. And if you count how many degrees of freedom it really has only 2 bosonic and fermionic oscillator degrees of freedom. So if you impose the usual physical state condition, basically all of these AdS3 × S3 oscillators get removed by the physical state condition, and you're just left behind with the degrees of freedom coming from the T4. And when you go through it carefully, what you find is that you reproduce exactly the single particle spectrum of the symmetric orbifold of T4, where the W cycle twisted sector of the symmetric orbifold comes from the W spectrally flowed sector on the worldsheet. And we haven't only reproduced the spectrum, we've also checked that the correlation functions matched exactly. So this is sort of 5 years worth of work and summarized in 3 slides, because what I want to explain to you is the generalization to AdS5 × S5. So given the fact that this works so nicely for AdS3 × S3, what we propose is that you simply double degrees of freedom you have 8 symplectic bosons and 8 free real fermions, and they generate U2,2/4. And after removing an overall U1, you get P as U2,2/4, which will guarantee that the space-time theory has the correct symmetry. So more concretely, this is have you seen before. So we have these ambitwistor fields, a couple of alpha runs the spinor index, alpha dot is the spinor index, A is a vector index, and these are the commutation relations you've seen before. Then the bilinears of these fields, they generate exactly U2,2/4. And then in order to obtain P as U2,2/4, you need to gauge by an overall U1 field, which in this case takes the simple form. Now, maybe you're not familiar with, but actually this is something that certainly the spin chain people know very, very well, because this is really how the oscillator construction of P as U2,2/4 works in terms of the spin chain degrees of freedom. And what this is really the affinization of that construction. So this is very, very familiar from the spin chain description of n equals to 4 superhang. And it's sort of pleasing to see that the world sheet sort of reproduces very much the sort of same structure as the spin chain. Okay, so that's these are the degrees of freedom. So now what do you have to do? Well, we claim that as for the case of AdS3, you have to introduce spectral flow. And as for the case of AdS3, what this means is that we define tilde modes, and they are defined in terms of the untilde modes by shifting the mode numbers up and down by W/2, where W will run over all the integers. And again, that acts as before. So what this means is the tilde modes act on the conventional, say, Nervish-Schwarz sector representation, on the Nervish-Schwarz sector ground state, but you interpret it in terms of the untilde modes. So for example, if you look at this formula here, you see the tilde modes, they will kill for R equals to a half and positive, which means that the mu modes will kill if R is greater or equal than W plus 1/2. And that will work similarly for all the modes whose mode number is shifted up. So this is mu dagger, psi dagger for 1 and 2, and psi for 3 and 4. Whereas the other ones, it gets shifted down. So there, for example, for lambda will kill this if R is equal to a half. So this will kill this if R is greater or equal than minus W minus 1/2. So this is just how you make sense of this spectrally flowed representation. So these are the modes that kill the vacuum. So you can ask which are the modes that don't kill the vacuum. Well, first of all, either of these modes will not kill the vacuum if R is less or equal than minus W plus 1/2, i.e. if it's R less than this number. But in addition, you have modes from the top line if R that are non-trivial acting on this ground state if R is less than equal to W minus 1/2. So you have some set of special wedge modes together with modes that you think of as being out of the wedge. So far, this is just the representation theory of this world sheet theory. And now our intuition is that for AdS3 cross S3, you had an n equals to 2 critical string that is part of the Berkowitz-Vaffaro-Witten description. Here we've doubled the degrees of freedom. So what we postulate is that there is an n equals to 4 superconformal symmetry on this world sheet theory. And what we postulate is that the physical state conditions are those that come from the n equals to 4 critical string. So you demand that all positive n equals to 4 modes kill physical states. Now, if you count this will remove 8 bosonic and 8 fermionic degrees of freedom. So we interpret this to mean that all out of the wedge modes get eliminated because these are exactly the 8 bosons, the 8 fermions. They exist sort of uniformly. They get removed by this n equals to 4 critical string. And what we postulate or claim is that what you're left with are these special wedge modes that come from the fact that you've twisted it. And this is somewhat similar to in this Berkowitz construction of having this sector with U1 flux, where there's also an equal number of generalized zero modes. So we want to think of these modes as generalized zero modes that survive even after we remove the negative modes by this n equals to 4 critical string condition. And then on the resulting wedge Fock space, you finally need to impose the residual gauge condition. So this condition I've explained to you before, that's just imposing the U1 condition that you would have to do anyway, irrespective of this physical state condition. And the other condition we think of as being similar to a Virasoro condition in light cone gauge. So W you should really think of as being P plus in the usual BMN type description of this background, because if you look at the charges of the ground state, it really has exactly the same charges SP plus in the BMN case. And then this condition you should think of as being something like L0 is equal to minus 2p minus p plus. So this coefficient is minus 2p minus, or rather plus 2p minus. And if you look at the BMN limit, then in the tensionless limit, you would think that this second term drops out, and you basically get that the 2p minus is just equal to an integer, and therefore that motivates that the condition of that kind should naturally arise upon doing this, this quantization. Okay, so if you believe that, then the rest of the argument that I explained to you earlier applies. So then you reproduce exactly the single trace spectrum of free supermills in 4 dimensions, where now the spectral flow parameter is identified with the number of fundamental fields in this that appear inside the trace. And we've also, I've presented to you this this general argument before, but we've also confirmed this by explicit calculations. So this is something we are very confident about. So once you have just these wedge modes together with this, oops, no, something has happened. If you have these wedge modes together with these residual gauge conditions, then you end up exactly with the spectrum of free supermills. So let me conclude and explain to you where we think we are. So the free field realization of the AdS3 crosses 3 worldsheet theory that's dual to the symmetric orbifold, that is something we really understand in great detail. So it's just a natural generalization to AdS5 cross S5. And with some assumption about the structure of the physical state condition, this is the black box we haven't quite managed to get under control. But if you believe that the outcome of that is this wedge modes types these residual gauge conditions, what we've managed to reproduce is the exact single trace spectrum of free supermills from our worldsheet model. And the way it works is that it looks like a string bit model in that you have twistorial valued string bits, and somehow these conditions conspire to give you reproduce exactly the n equals to 4 supermilli at the single trace operators. So with the assumption, with the proviso that we have to sort of firm up this quantization condition, this opens the door for a proof of the AdS CFT correspondence, because here we have a worldsheet theory that will reproduce free n equals to 4 supermills, and therefore, in some sense, as long as we can define some quantization condition that will lead to that, we have found a string theory that reproduces free supermills. So I think that is an important step forward. But clearly we are not yet done. So I mean, the first open issue is we should understand this physical state condition from first principles. What this will amount to is constructing, in our opinion, this n equals to 4 generators on the worldsheet. We believe that is very realistic. And then we would have to reproduce this BRST analysis of Berkowitz-Waffer-Witten applied to the 5-dimensional case. That is likely to be somewhat complicated because even in the 3-dimensional case, there is very little work that has been done on that. I mean, I recently, together with my new PhD student, Charash Naderi, we've managed to get the Berkowitz-Waffer-Witten cohomology a little bit better under control. And we are working towards understanding that sufficiently well that we will also be able to get the AdS5 cohomology under control. Then one thing I haven't explained to you is there's a very neat description of the AdS3 correlations functions, and that structure is very likely to generalize to AdS5. So that should allow us to study the correlation functions of AdS5. And in particular, that will allow us to analyze the perturbation away from the free case, because that will correspond to starting with this free theory and perturbing it on the worldsheet. But since the correlation functions are likely to be under very good control, we should really be able to do this calculation explicitly and then say derive the anomalous conformal dimension of the Konishi multiplet or whatever you want from this worldsheet model. And finally, it's a somewhat slightly unusual way of looking at the n equals to 4 spectrum. In particular, this L0 condition gives you a rather natural filtration of the n equals to 4 spectrum. It's a little bit different than what people have considered before. So that may be in itself an interesting perspective on the n equals to 4 spectrum. It also ties a little bit in with this sort of hexagon type way of calculating correlators. There also, it's important that the Young-Mills field is really split up into 2 bits. And that appears naturally in our context. So you could believe that the structure of correlation functions will very naturally tie together with the hexagon approach towards calculating correlators for n equals to 4. Anyway, I think my time is up, so I'll stop here, and I thank you for your attention.
Thank you very much for this very nice talk. So we are really perfectly in time. So are there some questions? I see. Well, Misha, or I think maybe Bo was even before. He was uploading.
Okay, thank you. So for a very nice talk. I was curious about this spectrally flowed story. When we introduced that, we thought about that as some sort of winding in AdS3. Do you have a corresponding picture in AdS5 and or any geometry?
Well, I mean, in some sense, you see, the winding really means that you have a W string bits, right? Because a W wound string is very similar to W many strings, and somehow you want to glue them together just like a string bit. So it's maybe not that unnatural to believe that something similar should arise from the point of view of the string bit approach towards understanding n equals to 4 supermills. The other point of view is that I think if you want to make sense of this PSU of this PSU 1,1/2 Weissman-Minowitz model, then I think simply by consistency on the world sheet, you have to introduce this spectrally flowed sector. I think that's the only way to make the modular integral the world sheet integral modular invariant. So I think while I understand where your motivation came from, somehow in this perspective, there is probably also a direct CFT justification why you need this spectrally flowed sector. In the symmetric orbifold, it's very much what you see. It's really winding, and that's exactly the twisted sector at the boundary. And somehow here we think of this as just producing the W string bit model.
Yeah, sorry. I mean, actually, we thought about this winding, but the motivation for us was also modular invariant. So we started actually from conformal field theory, but then I think it was clarified a lot by Maldacena and Oguri, which made this space-time picture clearer. So that's sort of what.
Right, but if you think about it, if you think about it from the point of view of the symmetric orbifold, the W spectrally flowed sector becomes the W twisted sector. So what does the W twisted sector looks like? It's basically a string that goes W times around until it comes back to itself. And that really looks like W copies of a string. So that are somehow glued together like a string bit. So that's the way we want to think about it. So if you want to have a string bit interpretation, that's where this spectral flow comes from. It's basically a way of gluing W copies together.
Okay, so it's more from the perspective of the boundary field theory than from the world sheet that you have winding. Is that?
Well, I mean, I think we were just, I mean, the way we got there is that we just tried to generalize what worked for AdS3 cross S3. We just followed our nose. I mean, AdS3 cross S3, we believe we have pretty much nailed. So let's take this, what we understand there, and try to follow your nose. How could the AdS5 cross S5 generalization look like? And basically, spectral flow is, everything came from spectral flow in AdS3 cross S3. So our intuition was that probably everything will come from spectrally flow in AdS5 cross S5. And that's what this picture would seem to suggest.
Yeah, that's great. Really interesting. Thank you.
Thank you. So I think we have time for a short question by Misha.
Okay, I want to ask whether you see the higher spin symmetries that were known for a long time to be associated with free super Young-Mills theory and n equal 4 in particular. So is it there? It's, I mean, the construction is pretty much
Absolutely.
the same in terms of.
Yeah, absolutely. It's totally there. And it comes from the W equals to 2 spectrally flowed sector. So it comes from the, as you know, I mean, it comes from the sector with 2 n equals to 4 super Young-Mills fields. So it comes from the 2 flowed spectrally flowed sector, and we reproduce exactly the higher spin fields. And again, they come exactly from the same spot as they come in AdS3 cross S3. In AdS3 cross S3, we also see the higher spin fields. They also come from, in this language, the W equals to 2 sector. And in fact, the W equals to 2 sector is just the BPS state. It's the Konishi multiplied and all the higher spin multiples.
I was asking not quite about higher spin fields, which are of course there, but about higher spin symmetry that acts on the free supermultiplet and then can be extended. So it should be, it is, I can see this, part of your construction.
Yeah, absolutely. Because I mean, this W-fold tensor product, the singleton representation is also a representation of the higher spin algebra. And therefore, whether you think of it in terms of PSU 2,2/4, or whether you think of it in terms of HS 2,2/4, it's the same representation. And the W-fold tensor product is the same representation. So absolutely, it has built this higher spin symmetry is sort of very manifestly built in.
Okay. Okay, I'll probably ask next in the discussion session then.